Other part of chapter 1, we're going to look at bonding and everything that carbon and other molecules like to do. So molecules want to be stable. They want to make a set number of bonds. Depending on what the atom is will determine how many bonds it can make. The atoms we're going to look at for the most part are going to follow the octet rule, except our hydrogen, which only wants to make one bond. All right. If my atom has a charge or a lone pair of electrons on it, this could cause a lot of instability in the molecule. So hydrogen wants to make one bond and only one bond. Carbon wants to make 4 total bonds. Okay. It has 4 lone electrons around it, 4 valence electrons to begin with, and it wants to use those up to make bonds. So it can make 4 individual bonds with something, okay, 4 different things like hydrogen. It can make a double bond and 2 single bonds. It can make 2 double bonds. It can make a triple bond and a single bond. Okay. What it can't do is make 4 bonds with one atom. Okay. It can't make 4 bonds. There's no such thing as a quadruple bond. But carbon wants to make 4 bonds. So the big thing is when you start drawing your structures out and everything, and you're drawing mechanisms from this point on, make sure your carbon always has 8 electrons around it. Make sure it only has 4 bonds. Where it gets tricky is when we start adding double bonds and you forget to remove hydrogens. Okay. Now, we look at the different types of reactive species of carbon, and we look at them in terms of stability. Okay. We have what's known as a carbocation, where they're short a lone pair. We have a radical, which there's a whole chapter we'll talk about radicals in Orgo 2. And then we have a carbanion, which has a lone pair and therefore a negative charge on carbon because carbon has an extra electron. Okay. If we're talking about stability of our reactive carbon species, the carbanion is the most stable because the octet rule is still in effect. Okay. I have 8 electrons around me. Yes, they're not bonding. Yes, I have a charge, so I'm not as stable as, let's say, this carbon up here. But I am more stable than this carbocation because the carbocation doesn't have any electrons around it extra. It only has the 2, 4, 6, and it's short 2 for that octet. So a carbanion is more stable than a carbocation. A carbocation, that means, will be a more reactive species looking to find electrons to complete the octet around carbon. Nitrogen, when we start talking about amines and amines and all things like that in nomenclature, nitrogen wants to make 3 bonds. Nitrogen prefers to have 3 bonds and a lone pair on it, just like here, or just like we see in ammonia. Can it make a 4th bond? Sure, it can make a 4th bond using both electrons from nitrogen. We call that a coordinate covalent bond. We talked about covalent bonds. Well, a coordinate covalent bond is a covalent bond where the 2 electrons come from one species, as opposed to a covalent bond that we're used to where 1 electron is brought in from one of the atoms and the other electron from the other. Here, nitrogen can make a coordinate covalent bond, but it always wants to make 3 bonds with a lone pair. Okay. Here it is with a plus charge. Okay, that's ammonium because it's making 4 bonds. It doesn't like to. Here it's short a bond with a lone pair. These are all relatively stable, not as stable as this because they still do complete the octet. Oxygen. Oxygen loves to have 2 bonds and 2 unshared pairs. Okay. Like here or here. But we can also see oxygen as hydronium, which we've seen in the past. as an acid. We could see it as hydroxide with a negative charge on it, but the octet, unlike the carbocation, all right, here, and the carbanion, okay, we have a completed octet here. Still have the octet like the carbanion, negative charge, not as stable as everything bonding. Halogens, no matter what the size of the halogen is, it'll always look to make one bond and have 3 unshared pairs. As you saw in Gen Chem, we could make multiple bonds with halogens under pressure and things like that, bromate and things like that. But we prefer them to have one bond, one lone pair, and as an ion have all 8 electrons around it. Phosphorus, okay, phosphorus is kind of like nitrogen. It really wants to make 3 bonds and have a lone pair on it, since it is in group 15, the nitrogen family. They're all going to act similar. But phosphorus could get crazy because phosphorus has an empty d orbital. So phosphorus can also make multiple bonds, 1, 2, 3, 4, 5 bonds, because it has the 5 electrons around it and can do some hybridization, which we're going to review in a little bit. Sulfur, same idea. Would love to do this. Be just like oxygen, but also has an empty d orbital sitting there, in the 3d, and can hybridize and make multiple bonds. So as we get bigger, we have more possibilities. You're going to see these linkages in DNA, all right, linking our phospholipid bilayers. All right. So let's talk about bond strength and bond lengths. All right, the number of bonds we make. Let me come over here. All right, so if we increase the number of bonds, we increase bond strength. And we decrease bond length. Okay. So the more bonds we make, the stronger the bonds are. So a single is the least number of bonds, therefore the least amount of strength, but has the longest length. A double bond is somewhere in between, and a triple bond has the most bonds, the most strength, but the shortest length. Okay. So what we call this bonding, and it is all dependent on what type of bonds and what we're bonded to, bond dissociation energy is the amount of energy required to break a bond in a homolytic way in the gas phase. What that means is, homolytic means when I break this bond, right here, what I'll do is I'll get my pen. When I break this bond, right there, one electron comes over here and one electron comes over here. Now this isn't the ideal way of breaking things, homolytic. All right, they usually break heterolytic, where one side takes both electrons and one side's short. We would create like a carbanion here and a carbo, or a hydrogen or a proton over here. But bond dissociation energy, how much energy that's required to break the bond, is usually measured, okay? What is the energy required to break a bond in a homolytic way where each side gets an electron? The energies that are required are all dependent on what the carbon is bonded to. Carbon in methane, which is essentially just a carbon bonded to a hydrogen, bonded to a hydrogen, bonded to another one, and bonded to one more. Okay, that's methane. Has a bonding energy or a bond dissociation energy of 104. kilocalories per mole, while ethane, which is this up here, to take that carbon away from this hydrogen, is 98. And it all has to do with the fact that it's carbon bonded to all hydrogens, or carbons bonded to another carbon bonded to the hydrogen. That plays a role. We'll talk about that later. It's something called the inductive effect. So if you put that in your, back of your brain when I bring that up later. Okay. So this is just showing the relationship between bond energies and bond lengths. You can't compare apples to oranges. You can't compare a nitrogen to hydrogen bond to a carbon to hydrogen bond to a carbon, an oxygen to hydrogen bond. They have to be relatively the same thing, I would say. How to put it here? Like I could compare a carbon to carbon bond with a carbon to carbon double bond with a carbon to carbon triple bond. And if we look at that, it's 81 for the energy of a single. And again, we're going to increase energy as our bonds go up, 145, 198. Then come over here and look at length. Bond length for a carbon to carbon bond is 1.54. Double bond, it's going to get smaller, 1.34. And triple bond, 1.20. I could do a carbon to nitrogen triple versus a carbon to nitrogen single, but comparing like a carbon oxygen single to a carbon triple bonded nitrogen, really difficult to do. What I do want you to focus on also is look at your halogens. Carbon to fluorine's energy, the more electronegative the atom is, the more energy there's going to be. Fluorine, then chlorine, then bromine, and iodine moving down group 17. Therefore, more energy, shorter length. Bond length gets bigger as my atom gets bigger and less electronegative. Do you need to memorize the values? No, but you should memorize the concepts. You should memorize the idea. So on an exam, if I said to you, you've got a carbon to chlorine bond and you're comparing it to a carbon to bromine bond, which one would you expect to be larger? Which one would you expect to have a greater energy? I wouldn't ask you, okay, what is the exact energy of a carbon to bromine bond? No. But I expect you to know that a carbon bonded to a more electronegative atom is going to have a greater energy. So the higher up a group, the more energy I'm going to have. Therefore, the smaller the length it would be. But I'm not going to ask for exact numbers. But I would expect you to know that the more bonds I make, the more energy I have, the shorter my length is. The bond I make is with the more electronegative atom, the more energy I'm going to have, the shorter my length is going to be. That I do expect you to know. Okay. So what can we say about this information? Stronger bonds are shorter. Bonds between hydrogen and carbon, nitrogen, or oxygen are strong. Bonds between carbon and nitrogen or carbon and oxygen are relatively strong. Carbon to a halogen become longer and weaker as the atomic number increases or as electronegativity decreases. And double and triple bonds are shorter and stronger than our normal single bonds. All right. Questions? Questions. Since I've been talking for about 10 minutes nonstop there. All right, and then we'll keep going. So let's talk about chemical formulas and how could we draw certain compounds. So you're given a formula of C2H6O, and we want to follow the rules that we talked about. Okay? And you could go the long route here. You can go the long route and do the Lewis structure like you were taught in, general chemistry, and that's fine. Some of the valence electrons, blah, blah, blah. But you could also follow the rules that were just stated. Carbon wants to make 4 bonds and have no lone pairs. Hydrogen wants to make 1 bond. Oxygen would prefer to make 2 bonds with 2 lone pairs on them. So how can we possibly draw this and make sure that we follow all those stability rules? Well, there's actually 2 ways to draw this. Okay, one is dimethyl ether on the left-hand side, where we plop the oxygen in the middle. And again, this structure doesn't show all the electrons there. Okay, so there's really, a pair here and a pair there, and same thing over here. Okay, but there's 2 ways. I could put the oxygen in the middle of the 2 carbons and link them up, and carbon's making 4 bonds, good. Each hydrogen's making 1 bond, good. Oxygen's making 2 bonds with 2 lone pairs, good. Or I could put the oxygen at the end. Carbon's making 4 bonds, hydrogens are making 1, oxygen's making 2 with its 2 lone pairs. One is dimethyl ether. You drink it, you die. One is ethanol. You drink it, you get drunk. Again, you could die in large quantities, but you drink even a small quantity of dimethyl ether and you're going to be in big trouble. We call these structural or constitutional isomers of one another. A structural or constitutional isomer, okay, is a structure, or structures it would be, that have the same chemical formula but have a different bonding arrangement. Okay. So a constitutional isomer, same structural formula, or I should say same chemical formula, different structural formula, different bonding arrangement. And C2H6O is one of those examples. Well, how do I know how many constitutional isomers are there for a substance? Well, you'd have to be told or look it up. But the more carbons I have, the more possibilities I have for isomers. Okay, so we have CH4 has 1, C2H6 only has 1 possibility, and these are known as hydrocarbons because all they contain is carbon and hydrogen. C4H10 has 2, C5H12 has 3, and so on. So let's talk about these for a little bit. Okay, how do I draw them? What do I do? How is it going to work? Well, I'm going to show you what I like to draw, which is the line structure way, which is the way we've been seeing on the slides. And there's also the skeletal way. Okay, I'll show you both. So if we look at C4H10, C4H10 has 2 structural isomers. C4H10. Okay, now, when you're drawing out carbon compounds, the way they work is the longest chain possible. Okay, so C4H10, we start off with 4 carbons. Okay, now there is a rule with my hydrocarbons. If I'm all singly bonded, I just missed it, 2N plus 2. The relationship in my hydrocarbons is whatever this value is, the hydrogens will be 2 times that value plus 2. So it's called the 2N plus 2 rule, where that is N. So this is C4H10, 4 times 2 plus 2. That's how you know you have all single bonds. If it's away from that, we'll talk about that in a second, but if it's different than that, you know you'll have double bonds possible in your structure. Okay. Now, I need 10 hydrogens. These two carbons in between already have two bonds, here and here and here and here. So they each need two hydrogens to complete the octet. The carbons on the outside need 3 to complete the octet. Okay, so there is C4H10, one possibility. 4 carbons in a row, all bonded to hydrogens, looks perfect. Well, according to that list, there's 2 possibilities. Well, the way you do this is you take a carbon off of your chain and then you add it somewhere else. So let's try that. Now, this is a different molecule. How could I tell? My longest chain, no matter which way I go. 1, 2, 3, 1, 2, 3, 1, 2, 3. Count up the number of hydrogens. I need 10. 3 here, 1, 2, 3. 3 up here, 1, 2, 3, that's 6. 1, 2, 3, that's 9. And 1 there for 10. These are both C4H10, but they are 2 different molecules. This is butane, and this is 2-methylpropane. Okay. Now, another way to draw these, not the skeletal, all right, or the line way, but known as the skeletal way. The skeletal way, you don't have to draw on the hydrogens. The skeletal way uses points. Each point is a carbon. Here's 1, 2, 3, 4 carbons. And if nothing's attached to them, it's assumed that there's hydrogens to complete the octet. Now, I draw it this way because I'm a biochemist, and this is what biochemists do. Organic chemists go straight down to this. I like this way because I could see everything. I think this way is going to make more sense when we do mechanisms, but this is also an accepted way. You'll see line way, and they call it line and Kugel. You'll see it that way. You'll see line and skeletal. This is known as the skeletal since you're just showing the backbone. How would we draw this one over here? Well, we would need 3 points. 1, 2, 3. 1, 2, 3. Oh, I did 4 there. There's our 3 points. 1, 2, 3. And off of this one, we would draw a line like so. And that would be it. So you have your 1, 2, 3 carbons. You have your other carbon there. So if you wanted to number them, let's just say 1, 2, and 3. And we would say, okay, this could be number 4. Here's 4. Here's 1, 2, and 3. And that would be the skeletal way of drawing that up there. Okay. Questions? So let's try another one. Let's try the next one on the list. C5H12. Okay. Let's try C5H12. According to the list, there should be 3 for C5H12. That's really not showing up well, is it? Go back to the black. All right, C5H12. So we start off with 5 carbons in a row. 1, 2, 3, 4, 5 carbons in a row. All right. Bring it a bit closer. Since it's the 2n plus 2 rule, I know I'm all singly bonded, so we're okay there. Now let's start drawing in our hydrogens. Now, here's another tip. With the skeletal, or with the line structure as I'm drawing here, you could just draw the lines in. And if you don't have anything attached, it's assumed it's a hydrogen. You don't have to draw in all your hydrogens. It's assumed that they are hydrogens. Okay. So, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens, and 5 carbons, and there's structure number 1. Now, I'm going to take a carbon off, and I'm going to draw out my next structure. I'm going to start with 4, and see how we do there. 2, 3, 4. Now, I need my 5th carbon. What I can't do is this, just to point it out. If I draw it there, I still have the same structure up here. 1, 2, 3, 4, 5. Longest chain, longest chain, longest chain. So it can't go there. Okay, so what if I put it here? All right, that could work. 1, 2, 3, 4 in a row. Let's see if we have 12 hydrogens. 1, 2, 3, 4, 5, 6. This one needs 1. There's 7, 8, 9, 10, 11, 12. Okay, so that one works out, and it's different than this one. Now, I know what you're thinking. Well, what if I did this? What if I try this over here and say, well, that was easy. Let me do this. Do. Put my hydrogens in. Put a carbon here. These two are the same compound. And I know what you're saying. Well, I'm numbering this 1, 2, 3, 4. Okay? So this one's on the 2nd carbon, this one's on the 3rd carbon. No, it's not. When you are numbering your carbons, you take the shortest distance to the thing that's not a hydrogen bonded to your carbon. So if I were numbering this chain, this would be a 1, 2, 3, 4 chain. If I were numbering this one, the numbering would go 1, 2, 3, 4, like that. So these are the exact same compounds. Don't let that happen. Okay? So if I can't do anything that way, then I must have to go with 3 maybe. So let's try 3. But where am I going to put the 2 other carbons? If I put it here, I still have a chain of 4. If I put it here, I'm going to have a chain of 4. So my only option is to do this. 1, 2, 3, 4, 5, 6 hydrogens, 7, 8, 9, 10, 11, 12. And there are my 3 isomers. We could call this my chain or this my chain. 1, 2, 3, like so. And we have our 3 isomers of C5H12. Structural constitutional isomers. Same chemical formula, different bonding arrangement. Okay. Questions on that? You tell me. I can't see your faces, so I don't know if you're all confused, frustrated, or anything. If you could just type no questions, then I would feel a lot better right now than what I do. All right, that makes me feel a lot better. Sheesh. You guys have me having heart palpitations here, and I'm a fat guy, as you can see, and that's not good. All right, good. All right, then what I want you to try for homework, all right, is draw all 4,111,846,763 isomers for C30H62. All right, sound good? If you start now, you might be done by the end of the year. But what you could try, if we're being realistic about it, you can try these two right here. These two are fun. And I know my idea of fun is way different than your idea. All right, then fun, but these will take you a little bit of time to think about. You can always email me. We could always go over it on Thursday. But try drawing the 5 isomers for C6H14 and try drawing the 9 isomers for C7H16. Okay? And if you're stuck on any of them, Google could be your friend. Just send me an email. We could figure it out and talk through it. Or if you want to, we can go over it first thing on Thursday. Okay? So try those. All right, let me continue on here. All right. How about if it's not a hydrocarbon that follows the 2N plus 2 rule? Let's say instead of being like C5H12, it says C5H10. Or instead of C5H10, it says, or C4H10, it says C4H6. Okay? A saturated carbon hydrocarbon means it's all carbon-to-carbon single bonds. All right? All carbon-to-carbon single bonds is the term saturated. Wow, my Google Hangouts is annoying the hell out of me right now. All right, so I'll mute that down. If I don't follow the N2N plus 2 rule, every time 2 hydrogens are removed, I either introduce a double bond, a ring structure, meaning that it's not a linear structure anymore. Okay. So let's look at an example of that. All right. I'm a hydrocarbon. We're only going to stick with hydrocarbons right now. Okay. But now my formula is so. All right. Let's do it this way. Under normal everyday conditions, I should be C3H8. Okay, that's known as propane. We'll worry about nomenclature in the next chapter, but I only have one isomer. There's only one way to draw it. There it is. Okay, if you want to do it the skeletal way, there you go. I know that looks silly, that's a carbon chain, but that's really a carbon chain. Okay, what if I gave you this instead, though? C3H6. Okay, well, my 2N plus 2 rule should mean I have 8 hydrogens. I'm taking 2 away. I only have 6. What this 6 indicates is either I have a double bond or I am cyclic. Okay. So, C3H6, 1, 2, 3. Now, I'm going to draw on a double bond somewhere. Right here. Either side, it doesn't matter. They're the same compound. I just want to point this out. If I do it this way, right? It's the same compound, okay? First thing that's not a hydrogen, a singly bonded hydrogen. I have this double bond. So this would be 1, 2, 3. This is, I'll make that a 1 like so. 1, 2, 3. So they're the same compound. All right, how many hydrogens do I need? This one needs 3 hydrogens. This one only needs 1. This one needs 2. 1, 2. And I drew it that way because of the double, but the 1's in the way. 1, 2, 3, 4, 5, 6. How about down here? This one needs 2. All right, it's the same thing. I'm just showing you that it's the same molecule. And this one needs 3, so they're the same thing. That's one way to draw C3H6. There is another way to draw it cyclic, meaning that it forms or isn't a linear chain. It actually forms a triangle. Each carbon is making 2 bonds, which means each carbon needs 2 hydrogens. Okay, so the first thing you check when you're asked to draw structural isomers of one another. Now, if I want to show this, okay, and I know this is going to be crazy, and I know it's going to be silly, but I'm going to talk you through this right now. They changed the rule since I took Orgo in 2001, is when I took Orgo. I taught it in grad school in 2004 to 2006. They changed it in between 2006 and like 2010, and I'll talk you through it. If I wanted to draw this way, all I would do is draw a triangle. There is, and now you can see why I don't like drawing it this way, but there is what we call cyclopropane. If I want to draw this one, guys, it's so silly. Yeah. It's like this. Okay, it's actually closer to this. I'm not a fan. But when I learned it, I used to draw... Okay, here. Let me do it this way. This is the new way. This is the old way. The old way was, I've got 3 carbons. Here's a double bond. So I'm drawing this one up here. Here's carbon 1. Here's carbon 2. Here's carbon 3. That was the old way. Then I open up the book when I start lecturing this in like 2012, and I'm like counting the carbons and something's wrong. They changed it. Here's carbon 1, and in a double bond to show that it's more linear and things like that, this is carbon 2, and here's carbon 3. But there's no point there, so it doesn't make any sense to me, but if you look in your book, that's what they're going to do for double bonds. That if a double bond exists, so let's say this is the drawing, right? And this is a double bond here. And we would say, okay, count the carbons. And I told you, every point's a carbon. 1, 2, 3, 4. No, there's really 6 here under the new way. There's 1 here. There's 1 here. There's 1 here. There's 1 there. There's 1 there. There's 1 there. I learned it that this was 4 carbons. But they changed the rule on the skeletal structure. For double bonds to show the lineality, I guess you would say, that's how you draw the double bonds. That there's actually a carbon here and a carbon here that aren't points, but they really are because the double bond's there. I know, silly. Okay. But here's where it gets even sillier. Okay? And I'm just pointing this out to you for future reference, because we're going to talk about this in nomenclature more and all of that. What if I had a triple bond? Okay, let's draw the same structure, right? And I draw a triple bond in. So you would say, okay, this is 1, 2, 3, 4, 5, 6. And I would say, nope, not now. If it's a triple bond, you go back to the old numbering. And the triple bond, this is really 1, 2, 3, 4. Now, don't shoot the messenger here. Okay? I'm just telling you someone got really bored or something and decided to change this. So I always stick to drawing this out. It might take a few extra seconds and it might take, some time to do it, but I always draw that out. All right, questions on this here, or double bonds or cyclic. Do we need another example? Because I could do another example of the cyclic or whatever it is you need. The more carbons you add and taking away hydrogens, the more options you have. Okay, the more options you'll have. For instance, if we do, let's do C4H8. We know it's short. There should be a double bond, or it should be cyclic, because it should be C4H10. All right, we start with 4. 1, 2, 3, 4. All right, and then we put in a double bond. I could put one here. All right, 1, 2, 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. I could also do this, draw in my 4, draw in a double bond. All right, I could do 1, 2, 1, 2, 3, 1, 1, 1, 2, 3. There's my 8, 6, 7, 8. Okay, I can make it cyclic, turn it into a square if I want to. Each one needs 2 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Good there. I could, let's see if I could. Because I'm just doing these off the top of my head here. What if I did that? Put a double bond there. 1, 2, 3, 4, 5, 6, 7, 8. That's a possibility. I can do, let's see if it would be different. This one, double bond there, and no, it wouldn't be different if I did that. Double bond there, single. Yeah, no, it would be the same structure. So, I mean, you have your possibilities. Okay? So the first thing you should do is check for your degrees of unsaturation if I have just a hydrocarbon by seeing if I follow that N plus 2. For each 2 hydrogens that I pull off, I introduce a double bond or a cyclic structure. If I pull 4 hydrogens off, I could have 2 double bonds or a triple bond, okay, present. All right, so this is our degrees of unsaturation, like I said. And how you find out your degrees of unsaturation? You put in your number of max hydrogens that you could possibly have. And by that, I mean your N plus 2, okay, the N plus 2 level. Okay, so the 2N plus 2 with the N, you could do that. That's your max. Minus how many does the structure actually have, divided by 2. And that'll figure out your degrees of unsaturation. So the example, we had C4H8. It should have, so if we used, let me just write it in here. if we used C4, and pardon my using a mouse to write penmanship, C4H8, the max we're supposed to have, 2n plus 2, is 10. What we actually have is 8. 10 minus 8 is 2. 2 divided by 2 is 1. 1 degree of unsaturation means I either have a double bond, okay, or a cyclic compound. Now, as they say, drawing larger molecules using the line or what they call the Kukl model, which is the one I like, it does get a little ridiculous. Look at this. So it could be easier to use the skeletal structure drawing. That double bond rule that I showed you only works for linear. If there was a double bond here, there's still only 6 carbons if it's cyclic. I don't know why. Every semester I do this, the students look at me and are like, why are you doing this to us? I'm not doing it to you. I remember when I first learned about it and my jaw dropped and I had to go check my old textbook to see, nope, that's not how I learned it, versus I'm thinking, did I remember it wrong? No, it got changed. I don't know where. I can't find it anywhere. But it definitely got changed from the book I used. I know, 100 years ago. I know the majority of you weren't born when I took organic, and that does make me sad. Really sad. Okay, so you can figure out the degrees of unsaturation. For each degree, you add a double bond, or make it cyclic, or if you have multiple degrees, you're talking triple bonds. Halogens, if they are in. Now we're getting away from hydrocarbons, and this is where I'm going to end the lecture. Okay? Halogens can make one bond, so they're used just like hydrogens. They don't change the value. So if I look at this, C5H11Cl1, okay? It's the same thing as being C5H12 because the chlorine only makes one bond, so that doesn't change anything. Oxygen, if it's in your formula, gets ignored, and you just focus on the carbons and the hydrogens. C6 should be C6H14. We're short 4. Our DU is 2. Nitrogen, okay, can make 3 bonds. Thus, for every nitrogen added, hydrogen has to be added to satisfy it. Okay. So nitrogen's a little funky, but C10H15 with a nitrogen has a DU of 4. Let's figure it out. C10 should have 22, right? So this should have, let me get my little pen here. This should have 22. C10 should be H22. Okay? If I'm doing my DU, max should be, oh, that should be a 22. Max should be 22 minus how many are actually there. Okay? There's 15. But I have to subtract 1 because 1 hydrogen is added for every nitrogen. Okay, so it ends up being 22 minus 15 minus 1 for the rule there. So for every nitrogen that's in the formula, subtract the hydrogen from, what did they call it here? Actual hydrogens, you subtract 1. So you do 22 minus 14 divided by 2, and that's where your 4 comes into play. So here we would have a bunch of double bonds or a triple bond and a double bond or a triple bond and a cyclic we'd have some kind of, crazy looking structure right now. All right, that's where I want to stop. So let me look in the book real quick to see if I can find examples of DU and practice problems of DU and all of that fun stuff. Acid base, we didn't. So I'm going to finish this in acid base on on what's today? Tuesday, so Thursday. I'm teaching 3 classes in the summer here at the same time, and I keep forgetting what day I'm in. But you know. All right, let's see here. Dipole moments, formal charge and resonance. Guys, I mean, if you want to try formal charge and all of that stuff and write structural formulas and things, you need more practice. Page 48, the homework, and this is one reason I like this book. Some people don't like this book. I like it because of the value, the cost. But, yeah, I mean, starting on page 48, I mean, we didn't do acid and base yet, but on page 48, all right, you could start with, you know, the structural formula problems at 1.43 and start looking. If there's something we didn't cover in class, don't worry about it. But you could go all the way, you know, to 1.47. That covers structural formula, what we did today, constitutional isomers. If you need practice on dipole moments and formal charge, okay, formal charge, what we did, what would have been Thursday, formal charge, resonance. All right. Dipole moments. That starts at 1.48 and continues on to 1.57. Okay. Yep, nomenclature comes up next. Isomers, here we are. Here we are. Okay. For isomer stuff, we're on more isomer stuff. Page 70. Don't worry about IUPAC naming and all of that stuff. So page 70 and 71 is isomers. It starts chapter 2. Our isomers. And let me look in the back of chapter 2 here. See if there's any problems with isomers that we can do. Okay, page 93, 2.24 to 2.27. Okay. All right, so that'll be that's some stuff you could try. Again, I don't collect homework. It's just for you to try if you think you need more practice. Okay. So page 70 to 71 is essentially the chapter information on isomers. Page 93 is the homework. This is the homework. You can look through the whole entire chapter 1 for formal charge, resonance and stuff like that.